Hey everyone, welcome back to the channel Code with AKJ. Today is day 50 of solving LeetCode 75 challenge, and today's problem is smallest number in infinite set, which is from priority queue module. So before moving to the problem statement, make sure to like this video, share it with your friends, comment your thoughts below, and subscribe to the channel so you never miss an update from this channel. So let's get started with our problem statement. So the problem statement says you have a set which contains all positive numbers, that is from 1 to infinity. Implement the smallest infinite set class, which has a constructor and two functions. So smallest infinite set initializes the smallest infinite set object to contain all the positive integers. Int pop smallest function removes and returns the smallest integer contained in the infinite set. And void add back function adds a positive integer num back into the infinite set if it is not already in the infinite set. So we need to design a data structure that initially contains all the positive integers, that is from 1 to infinite, and it supports two operations, that is pop smallest and void add back. So pop smallest removes and returns the smallest integer, whereas add back function adds num back if it was removed before. So let's see this given example. So in the input, we have been given a set of query. So based on this query, we need to perform operations on this given data structure. So the first query here is smallest infinite set, which generally tells us to initialize an object on which we need to perform a set of operations. The second query here is add back with the value 2, which means we need to add a value num2 inside our infinite set. So since the infinite set already has a positive integers initially, that is from 1 to infinite, so since 2 is already in the set, no changes are made. Next query here is pop smallest. So with this given query, we need to pop the smallest element from our infinite set. So we'll return 1 since 1 is the smallest number out of all the numbers inside our infinite set. So in the same way, we have been given set of queries inside our input, and based on these queries, we need to output the set of results. So this is all about problem statement. So let's start with our naive idea. So in our brute force approach, we can store all the numbers inside a list or a set. So let's consider this as a set. So initially, we'll store all the numbers from 1 to infinite. So according to our problem statement, the maximum number can be 1000. So we'll use a set and we'll store all 1000 numbers inside our set. And then we'll perform these operations based on our queries. So if the query is about adding the number inside our set, so if the query is about adding number 5 inside our set, so we'll check first inside our set if this number is already present in our set or not, and if it is not present, we'll push this particular number inside our set, and if it exists, we'll neglect this particular query. So since 5 is already exist in our set, no changes would be made to our set. So if our query is pop smallest, so generally set store all the numbers in ascending order. So the set dot begin function would give us the smallest number inside our set, which would be 1 in our case. So we'll return 1 in our pop smallest function query. So in this way, with the help of our set, by storing all the numbers initially, we can perform this add and pop smallest function easily. If the first query is pop smallest, so we'll return 1 and we'll remove 1 from our set. And after this pop smallest query, if we get a query like add num value, which is 1, and here in this case, since 1 is not present in our set, we'll add back this number inside our set, and our set contains values 1, 2, 3, 4, 5. So now let's understand the time and space complexity of this given approach and why this is not optimal. So generally the initialization operation, which generally stores all the numbers initially, that is from 1 to 2000, takes O of n time complexity because we prefill the set with numbers from 1 to 2000. And the pop smallest function generally takes O of log n. Since we are using a set, the operation of pushing the element back inside our set and popping the element from our set takes O of log n time complexity. And whereas the space complexity here is O of n. So the initialization takes O of n time complexity. Push and pop operation takes O of log n time complexity, whereas the space complexity takes O of n time complexity. So why is this not optimal? Because we cannot store infinite numbers. Also, inserting all the numbers up to a larger limit like 2000 is memory heavy. where we are trying to store all the numbers that is from 1 to 2000. So hence we need a better approach. So instead of storing all these numbers inside a set, we need a better approach to add and pop the smallest element from our infinite set. So before moving on to the better approach, let's try to code this naive approach. So in our brute force approach, since we are using set, so we'll initialize our set, which is public to all the functions, and inside our constructor we'll initialize and store all the values from 1 till 2000 inside our set. And inside our pop smallest function, since set stores all the numbers in ascending order, the set dot begin function would give us the pointer to the smallest element inside our set. We'll grab that value. Since set dot begin gives a pointer, if we add star to it, then it would give us the value. And after popping it, we'll remove that element from our set with the help of erase function, and we'll finally return that value. And inside our void add back function, we'll directly insert our num value inside our set. So in this way, we have designed a data structure which would perform all these queries with the help of our set, which initially store all the numbers inside our set, and based on the query, it performs a set of operations. So let's quickly run this code. It's working, so let's submit. As you can see, it works, but generally this is not optimal since we cannot store all the infinite numbers inside a set as it becomes memory heavy. So to optimize, we'll use two smart ideas. So we'll use a pointer which generally points to the next smallest element. So it generally keeps track of the next smallest integer that hasn't been popped yet, and initially it would be 1, and then after popping it generally moves to 2 and 3 and so on. So after every pop operation, this particular pointer moves one step ahead. So initially it would be pointing to 1. So after popping, pointer generally points to the next number. So we'll increment this pointer by 1. So after popping, this pointer would be pointing to 2. And again after popping, this pointer would be pointing to 3 and so on. So this way we don't need to store infinite numbers. We generally use this pointer variable to track the next smallest element that hasn't been popped yet. Next idea here is to use the min heap. So this is to handle numbers that are added back. So we use the min heap here. So heap gives us smallest number in O of log n time complexity, and hash set ensures we don't add duplicates. So we'll use min heap plus set, and set ensures that we don't add duplicate values inside our min heap. So with the help of these two ideas, we'll be able to track both the smallest element as well as adding back the value inside our min heap. Let's quickly dry run with an example to check how this particular approach works and why it is optimal than our brute force approach. So in our optimal approach, we'll use both min heap and as well as a set. With the help of a next pointer, which would be pointing to the next smallest element, we'll take a next smallest pointer, which would be initially pointing to 1. We'll take a set, which will help us to handle with duplicates, and we will also take a help of a min heap, which would give us the smallest element out of all the numbers. So initially our query is smallest infinite set. So with the help of this query, we'll initialize our pointer, that is next pointer, with 1, and the next query here is add back. Whenever we are trying to add back a value, we'll check two conditions. That is, one condition would be to check if we already have this value inside our set, and another condition here would be that this given num's value which is going to be added should be less than the next pointer. So this num value should be less than the next pointer, as well as it should not be present inside our set. That is, st.find should be equal to st.end. So if it satisfies these two conditions, then we can add this given number inside our set as well as in our heap. So the number here is 2. We'll check whether this number is present inside our set or not. So initially it is not present inside our set, but if we compare it with our next pointer, which is initially pointing to 1, so since 2 is greater than 1, so this condition does not satisfy, so we'll return null. As you can see here, the output is here null. Coming to the third query, pop smallest. So for this given pop smallest query, we will first check inside our min heap we have a value inside our heap or not. Heap contains value, return the topmost value of our min heap, which generally gives us the smallest element inside our heap. And if it is empty, then we'll return the next smallest element and increment the next smallest element. So for this case, since our min heap is empty, we'll directly return our next pointer, which is pointing to the smallest number, so which is 1. So we'll return 1 in our case, and we'll increment our next pointer to 2, which means the next smallest pointer here is 2. So coming to the next query, which is again pop smallest. So since our min heap is empty, we'll directly return our next pointer, which is 2, and we'll increment our next pointer, which is pointing to 3. So again, next query is pop smallest. So min heap is empty, so we'll return our next pointer directly, which is pointing to 3, which gives us 3, and we'll increment our next pointer 4. So now the next query here is add back with value 1. For this query, whether this value is present in our set or not. So since our set is empty, which means 1 is not present in our set, as well as 1 is less than 4, which is the next pointer. So we can add this number inside our heap and set. So our heap contains value 1 and our set contains value 1. And after inserting, we'll directly return null. So our next query here is pop smallest. So whenever the query is pop smallest, we'll first check the min heap value, then we'll check the next pointer. So in this case, our heap contains a value which is 1. So the topmost value gives us the minimum value inside our heap. So the topmost value here is 1. So we'll pop this from our min heap and we'll directly return the smallest element, which is 1. So for this pop smallest query, our answer would be 1. And we'll also remove this from our set as well. So the next query here is pop smallest again. So we'll first check the min heap value. So since min heap again became empty, so we'll directly return our next pointer value, which is pointing to 4. So we'll return 4 and we'll increment our next pointer, which is pointing to 5. And again, the last query here is pop smallest. So the min heap is empty and we'll return the next pointer, which is pointing to 5, and we'll increment our next pointer, which is 6. So the output would be 5. So in this way, with the help of our next pointer and with the help of our min heap and set, we are not storing all the values initially, which is from 1 to 2000 or 1 to infinite. So with the help of just next pointer, which would be pointing to the next smallest element, and with the help of min heap, which would give us the smallest element, and with the help of a set, which will handle the duplicates while adding back inside our min heap and set. Let's look at our initialization operation. So initialization takes generally O of 1 time complexity, as we are just setting a variable which is next smallest variable, which would be initially pointing to 1. So it generally takes O of 1 time complexity. So coming to the pop smallest function, so if heap is not empty, it generally takes O of log k time complexity, and if heap is empty, we'll directly returning the next pointer, so it generally takes O of 1 time complexity. And coming to the next operation, that is add back, it takes log k time complexity to push the value inside our heap. And finally, coming to the space complexity, it generally takes O of k time complexity, as heap and set store only re-added numbers, not the entire infinite numbers. And finally, coming to the scalability, we can handle infinite sequence correctly, as we are trying to use simple pointer, which will be incrementing after each and every pop operation. So in this way, with the help of these two, min heap as well as set, and with a smart idea of using a pointer to handle the infinite numbers, we have successfully solved this problem statement in less time complexity, which is far more better than our brute force approach. So let's quickly code this approach and let's submit. So let's quickly code our optimal approach. So we'll define all the pointers and the data structures we are using in our optimal approach. So first would be the variable next to smallest. We'll use a min heap priority queue. We'll also use a set to handle duplicate values. And in our initialization function, we will initialize our next smallest pointer, which will be pointing to 1. In our pop smallest function, we'll first check if min heap is empty or not. So if it is not empty, we'll grab the topmost value, we'll pop it from the min heap, as well as we'll pop it from set and we'll finally return that value. And after every pop operation, we'll increment our next smallest pointer. So if min heap is not empty, we'll use these operations, and if it is empty, we'll directly return our next smallest element. Coming to the add back function, before inserting this value inside our heap and set, we have to check two conditions. That is, if this given number is not present inside our set, as well as this number should be less than the next smallest number. So if it is, we'll push this number inside our heap as well as inside our set. So this is the code for our optimal approach. So let's quickly run this code. It's working, so let's submit. As you can see, this approach gives a successful submission, but when we compare it with our brute force approach, the time complexity is far more better than the brute force approach. And that's it for day 50 of LeetCode 75 challenge. So we started with a brute force solution, understood its limitations, and then we have optimized it using a pointer plus min heap plus set. So if you found this explanation helpful, don't forget to like this video, share it with your friends, drop a comment with your thoughts, and subscribe to the channel so you never miss a daily coding challenge. So I'll see you in the next video. Thank you.